आपण Rathore sir, we are live. We are ready to go, sir.
Okay.
સર કોઈ પણ લેંગ્વેજમાં ચાલશે, હિન્દી,
Okay.
ઇંગ્લિશ, ગુજરાતી.
Good afternoon, all. Myself, Dr. K.V. Rathore, Head of Mechanical Engineering Department from RNG Patel Institute of Technology. Heartily welcomes you all on the third webinar of Mechanical Engineering Department and 11th webinar of the college of the series 2 under SSIP cell. The topic of today's webinar is overview of meshing in ANSYS, and to present such an important webinar, we have with us Mr. Anand Mistry, founder and director of Aspire Designs from Vivinagar. And to know more about Anand Mistry, I would like to request Professor Nirav C. Rathore to give brief introductions of today's speaker. Over to you, Nirav Singh.
Thank you, sir. Good afternoon, all the viewers, for the webinar on introduction of meshing in ANSYS. Before starting the session, let me introduce our today's expert, Mr. Anand Mistry, sir. Anand sir is founder and director of at Aspire Designs Vivinagar, that is designing institute targeting academics as well as service, as well as it provides services to various industries. Sir has various software skills like PTC Creo, ANSYS, ANSYS CFD Fluent, SolidWorks. Sir has more than 10 years of experience in this field. Let me quickly brief you about Aspire Design achievements first. Aspire Design was awarded most consistent authorized training center in South Asia from PTC University, that is located in USA, United States of America, in 2015, 2016, 2017, and 2018. It is one of the two authorized channel training partner from ANSYS in India. Aspire Design, it is first ANSYS authorized training center in Gujarat, that is by ANSYS. Now, we all know that discretization is the very important steps in FEA. So the objective of today's webinar is how we can improve the quality of mesh, and hence how we can improve the result. So without wasting the time, let me switch over to Mr. Anand Mistry, sir, for today's session. Over to you, Anand, sir.
Thank you very much, sir, and welcome you all in this today's webinar. And today's webinar, we have a topic of overview of ANSYS, specifically for meshing criteria. As you can see in ANSYS, the meshing is a very critical part for the analysis, in which you discretize the model for the analysis. But why meshing is necessary? Because as you know, and as you have studied in your diploma and degree courses curriculums, and specifically in machine design components, the basic shapes like circle, rectangle, square, we have the equations to solve for its area, solve for its total volumes, and all other entities. We also have standard equations for beams and other struts, structures, nut bolts, and other threaded entities. We have it all. But as we can see in the industry, we have multiple components assembled in a single machine, and when the machine is being operated at a specific loading or a specific speed, we don't know how the machine is going to react to that force, react to that loading. To check that, we do the simulation process virtually in our computer systems based on different platforms like ANSYS, Abacus, then COMSOL. We have many. So what basically this software does is they divide the whole machine or whole component into n number of specific small elements which shape that we are known, like triangular, then hexagon, then square, rectangular. Okay, and what it does is it solve it one by one, element by element. Those single entities are called elements. And there are different methods for different physics to solve it. Like if you are solving it for the thermal condition, then the meshing will be different. If you are solving it for the structural condition, then meshing is different. If you solve it for fluid conditions, then meshing is different. So in today's topics, we are specifically focusing on the structural side. That if you want to solve a structural problem, then how you should mass it, how you should discretize the model so you can get nearby accurate result for the simulation. Okay. In ANSYS, mesh settings can be divided into two different parts. First part is the global mesh setting and the second part is the local mesh setting. In global mesh setting, multiple sub options are there like display style, then physics preference. As we discussed earlier, there are different physics and according to those physics, the meshing criteria changes. Then element order, then element size, then the adaptive sizing feature, the resolution of adaptive sizing, then the curvature and proximity. And for local mesh settings, there are multiple methods available, which are individual commands that you can impose on the global mesh setting. Once you have set up of specific parameters for the global mesh setting, then you apply this local mesh setting to either the whole assembly, or you can go for specific component, or you can go for specific surface, or you can go for specific edge, or to the minute detail you can control a specific endpoint or a vertex also in the local mesh setting. Okay, now so we will move to the ANSYS window. As you can see over here, I have created specific different systems for the meshing procedure. How we can do that? Like if we take a specific static structural meshing and analysis system, you can see it consists of total different parts which were joined together, and we have to follow them step by step. The first step is the physics that we are solving for. In our case, it is structural, static structural. Then the second step is the engineering data. In engineering data, you define the materials which will be used in your analysis system. Like you have some aluminum alloys, then you have some structural, static structural steel materials, then you have some copper components, then you have some brass components. So what you do, you basically define all the material and its properties in this engineering data. Engineering data has also a specific ANSYS library available, and you can use ready-made materials from that also. Then the third step is the geometry. Geometry has multiple options. Either you can create a geometry in ANSYS itself, or you can import the geometry from external CAD software or CAD solutions that you might have. Like you have AutoCAD, you can import from that. You have PTC Creo, you can import from that. If you have Dassault system, SolidWorks, you can import from that too. You can import from Dassault Katia also. If you have Siemens Annex, you can import that too. So n numbers of possibilities are there in the geometry part. Now moving on to the fourth part, and in fourth part we are peaking today, that is the model. Means the discretization of the model into the finite number of elements. That's why this methodology is called finite element analysis, FEA. After that, the fifth step is the step. As you can see in the step, a red arrow and a green arrow is showing that external loading conditions are being applied to the model. And in the green arrow, it is showing us that somewhat output parameters are also being defined in the setup. That what results we need. We need the stress contour plots, or we need the total deformation plot, or we need a specific factor of safety plot. So we have to define that in the setup step. Then the next step is the solution. In solution, the ANSYS software comes in picture. In the background, it will solve all the mathematical formulations for our model, and it will solve the whole calculations. And after that, the seventh step is the results. Once that entire geometry, entire model is solved, then the result will come in picture, and in result we will post process, we will see the results and interpret that from which location it is being failing, or is our component is safe or not. Okay, so how to start? Basically, we'll open a geometry window first. In geometry window, it will open a specific modeling platform of ANSYS in which you can model your own entity. Okay, there are two main modeling platforms available in ANSYS. The first one is the Design Modeler, which was legacy platform, and it was based on NX. And the second platform that currently we are using is called Space Claim. Space Claim is a direct modeler, and it doesn't have any kind of what we say feature tree or history available of the commands that you do. Okay, basically a simple tool is provided to sketch it and to make it a solid. Let's say if I want to make two components, a cylindrical component and a rectangular box, top of each other. So what we'll do, we'll go to simple rectangle sketch, we'll go to sketching, and we will sketch a rectangle from its center point having some specific values like 25 by 45, and press enter. Once that is created, it will be converted into sketch. If you see in the back, I'll go back one step. You can see over here we have a specific sketch entity available, and that is also showing in the curves tree that we have 4 lines available. Okay, and it's a close sketch. So once it's a close sketch and you have created independent lines, if you go to basically a 3D mode, then it will combine all those 4 lines and convert that close entity into a surface. So we have been going from 1D to 2D. First our sketch was 1D. Okay, only one dimension was there because we were sketching on a specific plane and no other parameters were there. In the 2D, now we have 2 parameters available for this sketch. We have filled up a surface. So surface has a height and a width. Okay, now if we go to pull command, and in pull command what we can do is we can add a third dimension. Like we previously had x dimension and z dimension available, and now we add a third dimension, y dimension. So now it is a proper 3D solid. Once that is being generated, you can see it will automatically convert that thing into a solid. So we have converted our first sketch into surface, and from surface into solid. So this is our first step. Now we can right click it and move it to a new component. Okay, we can name it as a rectangle. Now again, I'll go to sketch mode, and in sketching I will select the top surface of the rectangle, and above top surface I will draw a circle of a specific diameter. Done. Now we will back go to pull, so it will automatically go to 3D mode. We have a surface available now from the sketch, and we will add some dimensions to it. Okay, and for the sake of changing the different components, we'll change the color of an entire model. So you can differentiate two different components, component number 1 and component number 2. This is our second component. Now we'll move it to another one, that is our cylinder. So now we have two different components in our design, and you can see the icon has been changed to an assembly. Okay, In ANSYS, you do not need to save the model once you are working in the ANSYS environment. Simply close that window. It will automatically save the design and it will automatically move that component to the next step, which is meshing. Now you can see there is a refresh button available on the meshing. So double click it. So it will open a meshing window. And in meshing window, we are going to do a specific task based on local mesh settings and global mesh settings. So now, as you can see, we have different portions in our window. So okay, so first window is the outline one. In outline, you will see what are the things which have been generated for my project. Then in the right hand side, you have a detail column, and in top, you have a context toolbar. This toolbar is automatically updated based on the option you choose. Okay, if I choose the geometry, then I will have all the commands of geometry. If I choose the material, then I have options of material. If I choose the coordinate system, then I have the options of coordinate system. And if we go to mesh, then we have the options of mesh. And as soon as I click mesh, I have a specific details of mesh window in this column. So these all settings, the details of mesh, is called the global mesh settings. And as we have seen previously in the slide, the global mesh setting has some options like first one display style, then the second physics preference, then third element order, then element size. Then if we drop down, then we have much more options for adaptive sizing, then the resolution of adaptive sizing, then mesh defeaturing sizing. Then if we close the adaptive sizing, okay, then we have two other options, that is the curvature and the proximity. Don't worry, we'll go one by one. So first we'll check what are the options available in the global mesh setting. So first one is the display style. If we click the display style, then you have a drop down menu in which it will show you the different element quality criterias available to display. So if we took a element quality option, for that we have to create a mesh. So simply we will generate a rough mesh over here. Okay, as it is being generated, now you can see the element quality is being shown as we have chosen the option display style element quality. The quality which is in blue, as you can see, which is 0.99928 is the maximum quality available, and the worst quality available is 0.77, which is shown in red. So generally we tends to go for the highest possible element quality achievable for our model, and we can apply different mesh settings based on global mesh setting or local mesh setting and achieve maximum number of elements to be having higher quality. Then the second option is aspect ratio. You will see all these things in details once you know the theory of it. Okay, just to overview it, we are going back to the geometry setting. Now, in that, the first thing of the default setting is mechanical. What is that? We have different physics available at our disposal, like mechanical, then non-linear mechanical. Non-linearity can be of different types, like material non-linearity is there, then external loading non-linearity is there, then contact non-linearity is there. multiple nonlinearities are possible. So if you are solving a nonlinear analysis, then you have to choose the physics preference to be nonlinear mechanical. Then electromagnetics is also there. If you pass a current through a specific channel and you want to see the magnetic properties of it, that how much strength of magnetic field is being generated, or in which direction the magnetic field is rotating, you can check that in that physics, which is called electromagnetics, and you have to change the physics according to that. Then CFD is there. CFD means computational fluid dynamics. So if you are going for an internal flow inside a pipe or an external flow, like if you are wind tunnel testing of some external body of a car or any other entities, or you are specifically analyzing a blade profile or an aerofoil profile, at that time CFD will be helpful. Then the explicit dynamics. The explicit physics is specifically used when you are crashing something, you are breaking something in the simulation. At that time, explicit is used. And the last one is the hydrodynamics. Hydrodynamics is basically a combination of CFD and mechanical. So for our simulation, we are going for the mechanical. Then you have an option of element order. Element order are of two types, linear and quadratic. The linear element order means if we choose a specific element, at that time only two elements are being given per entity, first and second. But if we go for quadratic element and we update the mesh, what quadratic element does is it will create two endpoint elements, but it will create one also midpoint element too. So if you are using this analysis for higher degree of accuracy, at that time you will be needing all three elements for the simulation to capture the geometry properly. Okay, so at that time you will use a quadratic element, and if you use the linear element type and will generate the mesh again, we have to update it. Only two elements are being generated. Each element will have its own equation, and that equation will be solved from single order to second order to third order. It will go up to third order equations. Okay, so that is our element order. Now the rest is element size. Element size is the maximum possible size available for our model, that in which we want to discretize it. Like for this analysis, if we choose a 1 mm element and we'll generate the mesh, so what it will do, a maximum size of element of 1 mm by 1 mm by 1 mm will be generated, not more than that. This is the maximum possible element size given. Elements can be lower than 1 mm. If it is possible, then it can be lower than 1 mm, but not greater than 1 mm. This is the maximum possible size which we can give. Okay, and go, if you want to go back to default, then simply put 0 and press enter, so it will automatically go back to default value. Then we have the option of adaptive sizing. Now, the adaptive sizing has been using the ANSYS algorithm for creating the model, finite element meshed model since a long time. And as the ANSYS version increases day by day, a new update arrives. This adaptive sizing feature is getting much more capability to analyze and mesh the model effectively. Okay, and the adaptive sizing can be controlled based on the resolution. Resolution minimum can be gone up to -1 and maximum can be gone up to 7. 7 is the maximum resolution available. So what does that resolution does is, what resolution actually does is it will check the model automatically, okay, and depending on the model geometry, it will try to create a finer mesh. It will take the control of element size, element type in its own hands, and it will try to give us the best possible mesh for our model. So if we choose resolution 7, before going to that, the default statistics of the element is 1554 nodes and 1077 elements which were being generated when we have the default setting available. Now from going resolution 2 to resolution 7, if we generate the mesh again according to the new refinement model, now you can see it has created more and more finer mesh, and it has created more number of nodes and more number of elements. So it will increase the accuracy of the simulation. Okay. So this is our adaptive sizing procedure. In adaptive sizing, you have multiple options like mesh defeaturing. Defeaturing means if you have previously encountered and introduced some features into your models, like if you have given some fillets over there, if you have given some chamfers in your model, and at the time of meshing you want to ignore those entities and make the model more simplified so that a higher quality mesh can be generated quickly. At that time, mesh defeaturing feature has been utilized. So if you have created a chamfer of edge length of 4 mm and you want to defeature it in the meshing criteria, then over here in defeaturing size, you have to give a little bit higher value than that 4 mm, like you can give 4.1 mm. Then at that ANSYS meshing engine, it will calculate that edge length up to 4 mm, and it will give the command to the measure engine that okay, this entity has to be neglected in the time of meshing. Okay, that is our defeaturing. Now if you go back to our main default resolution, and we can see the transition over here, the transition detail. Okay, in transition, the size of element from being small element to a bigger element, the growth of it is called the transition. If the transition is fast, then the growth will be higher. The element will grow from smaller to bigger size very quickly. If we go to slow transition, then it will create multiple elements before changing it to a higher size. Then we have the span angle. What span angle is? There is a specific angle between the two edges of the element, because these three edges, these four endpoint, the vertices of the element are being having some kind of angle between them. To increase this angle, we have to use the coarse span angle feature, and to reduce it, we can use the fine span angle center. So what it will do is it will reduce that element degree and it will give us the finer element with a low span angle. Then we have an option of initial sizing seed. This feature is worked when you have large assembly of like 1000, 2000 components. And at that time, somewhat elements are having some values in meters. And if you are using some bolting or some fasteners in that, at that time the fasteners might have a value of M16 or M18 or M20, like 20 mm. So compared to those meters value, like if we take a 2 meter component, then it will be converted into 2000 mm, and 2000 to 20 mm. There's a huge difference. So what this meshing engine does is it will compare automatic multiple components, that what is the size of one component compared to the other, and based on that it will create a mesh for that entity. So this is our initial size seed. Okay, I'll show that option in another one example. So we'll move on to another example, which is specifically being created for the global mesh. Okay, so now as you can see over here, we have a component with bolted assembly having one main body, then a bolt, then a left side washer and a right side washer. Now as you can see in the details, if we go to body, we can check the properties of the body and we have a specific volume which is 3.33 into 10 raised to 5 millimeter cube. And compared to that, if we go to a washer body, which has a volume of only 2749 millimeter cube. So if we go to mesh, if we go to sizing, and if we initialize the seed based on assembly and create a mesh, then what it will do is it will create a mesh of the geometry compared to other bodies available to it. Okay, and so as so the mesh sizing on this body has been a coarse mesh. But if we change that based on part, so what it will do, it will scan part by part for the assembly for the initial mesh element sizing, and it will mesh it according to that. So if we go on based on part, now you can see it has divided that element into two different elements based on the part. And you can see that also over here, it has created two different parts for the same thing. So this is basically a part based seeding or a what we say assembly based seeding. Okay. Now for higher quality of mesh, we can change the meshing method based on adaptive sizing on or off. If we turn off the adaptive sizing, then we have two options. The first option is the capture curvature. Okay, so as you can see in our model over here, we have a curvature over here, then we have a curvature over here, we have curvature over here. Okay, in short, any line which is not straight is called a curvature. So if we turn on that capture curvature option and we'll generate the mesh, you can see the change that it has created more number of elements at the curvature location to capture that curvature phenomena properly. Okay, that is called the curvature capture curvature option. Then the second option is capture proximity. Proximity means if a two components or a two faces or a two edges or a face and a edge is close to each other compared to other sizing of the component, it will capture that phenomena and it will try to mesh higher, means densely in that location to capture the effect of stress distribution or a deformation distribution effectively. It will generate a higher number of mesh in that location. So as you can see over here, we have a one edge over here going down and we have another edge over here going down. So as you can see, it has created more number of elements in this region compared to the whole assembly. The whole assembly won't have much higher components, but whenever there is a two edges or two surfaces getting close to each other, it will create a finer mesh. And that is also seen over here, that one edge is this one and one edge is this one. Two edges are being joined together at this location, so it will try to create a finer mesh in that location. That is called the proximity. Okay, so these are the basic options of global mesh settings. Okay, now we'll move on to the local mesh settings. Okay, so I'll be using the same model for the meshing of local sizing also. So first of all, what we have to do is generate a specific rough mesh based on the global settings. And now we'll go to different criterias. Okay, so for this part, what we'll do, we will hide all other bodies and we will target on this single body only, the bolt. Okay, so as you can see from the global mesh setting, it has created some okay mesh, and which can't be used in simulation as it has a very rough quality. So we need to refine that. For refining this entity, we have an option of local mesh settings in terms of local mesh control, as you can see over here in the topmost portion. So the first one is the method. Okay, in method, what we have to do, we have to first specify which body we want to work on. Once we apply that, different methods has been shown. The first one is the automatic. What automatic does is, it will do the same thing as adaptive meshing does in the global settings. Then we have a second option of tetrahedrons. Now what tetrahedron does is, it will try to create triangular mesh for that body. It will try to create a triangular mesh for that body if the body is being generated as a hexahedral body. Then we have second option of hex dominant. What hex dominant is does, that it will try to merge the entire body into hexagons, means square elements. But it is not recommended to use this entity, as if you go for hex dominant meshing, the elements which are being generated inside that body will cause rupture, and these are very bad quality elements. If you see elements from the outside, it is good and it is nice to have such mesh possible, but if we see the inside elements, the all elements have been ruptured. So it is not feasible and it is not what we say, advisable to use the hex dominant mesh until and unless it is required. Then we have an option of sweep mesh. What sweep mesh does is, it will do the same thing possible what a sweeping entity can do. For the sweep mesh, you will go to the washer part, because washer part will be easy to sweep it. Okay. Then we have an option of multi-zone mesh. Multi-zone mesh is generally a very good idea to mesh a complex component. So what it will do is, it will divide this bolt into two parts. First one is the cylinder and the second one is the hexagon. Okay, and it will mesh it independently, and then it will join the mesh of two entities. So if we update the mesh of this entity, then you can see a single entity mesh of cylinder is done and a single entity of mesh is of hexagon is done. And now as you can see from the surface, it has directly created the same mesh elements. Okay, this same mesh element of the bottom side. So what it does is it will split up the body into known components which are easier to mesh, and then it will create a finer mesh for the body, and it will create a higher quality of mesh. As you can see, this mesh quality is way higher compared to the hex dominant. You have a uniform elements inside as well as outside. So it is better to use a hex dominant mesh. Okay, this is our first local mesh setting, which is called method. Okay, so we'll show all the components and we'll choose method specifically for the washer body. Okay, now we'll hide other components, and in that method we'll go for sweep option. And what we will do in sweep option, that we will divide this whole entity. As you can see in this mesh, it has not been divided into multiple components. But in sweep method, we have an option of number of divisions. Okay, as you can see over here, you have an option of sweep number of divisions. So what it will do is it will divide that entity into the number of divisions that we provide over here. So if we give it a 5 number of divisions, now you can see in the mesh it has created 5 different divisions. Okay, so 5 different divisions are there: 1 2 3 4 5. So whenever you are generating a mesh for specific body which is sweepable, you know that this face is directly being swept to the other side. At that time, you can use the sweep method and you can give total number of divisions. And at that time, you can have a finer mesh compared to the mesh which is being generated without the sweep method. You can see that option over here. Okay, so the green body has a sweep method with 5 number of division, and the brown body doesn't have any kind of control. But what we can do is we can add sizing to it. Now this is the second local mesh setting, which is sizing. What sizing does is sizing can be divided into number of selections. Like if you have multiple faces selected, then the sizing will convert into face sizing. If you have selected number of bodies, then it will convert to body sizing. If you have selected a specific age, then it will convert to age sizing. And if you have selected a specific point, or what we call in ANSYS vertex, it will convert to vertex sizing. What we'll do is we'll select the whole body, go to sizing and select the sizing. As you can see over here, it has converted that into body sizing. And now in body sizing, we can specify the mesh size for it. So what we'll do, we select the body and generate the mesh for that body with body sizing of 0.5 mm. And now you can see our entire model has been selected with the maximum number of element size to be 0.5 mm, and it won't affect any other body. As you can see in here, it won't affect our whole assembly. It will work only and only on a single body that we have selected. Okay, so we can try again for our top entity also a method for this body to be a multi-zone model. Okay, multi-zone has failed. Great, delete it. Then we can apply a body sizing. We have another option, like if you want to go for 5 mm elements and mesh it. Okay, now we have a better mesh. Now if we go to again our bolt specifically, in the bolt as you can see, the cylindrical entity elements are not being what we say arranged properly. So you can add one more local options which is called face meshing. We select the face, apply and generate the mesh. So what it will do is it will try to arrange the elements properly. Now you can see it has been arranged properly. But only 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 elements are there in the circle. I need much more refinement. So what we'll do, we'll go to edge sizing. We'll select the edge and click sizing. So now as you can see, we have an option of edge sizing, and in that we have an option of number of divisions, that this circular entity should be divided into how much number of divisions possible. So let's say 20 elements. It will show you a preview of 20 elements. Okay, let's go a bit finer, 40 elements. Okay, so it has been divided into 40 different elements, and then we generate the mesh. Now you can see it has a specifically mapped mesh which is being arranged properly, and it has 40 number of divisions throughout the body, and that will continue on the top side also, as you can see over here, because we have created a multi-zone model for this one. So it will create a multi-zone model mesh at that location also, and a specific edge sizing of that side also. Now we'll go to context sizing. If we see in this location, there is a contact between bolt surface over here and a washer surface over here. There is a specific contact is there. So if we go to contact, we'll rename it based on definition. So you can see over here there is a connection of bolt and washer, and there is a connection of bolt and washer over here. So now we will drag and drop that bolt and washer connection to mesh. So it will create a specific contact sizing, and we'll hide all other bodies. We'll take only the bolted body, and in contact sizing we can define the element size like 0.1 mm or 0.5 mm will be great, and generate. Okay, so once that is generated, it has created this entire surface with a zero point 0.5 mm. Okay, if we check another bonded connection between a washer, okay, show all. Okay, this body has some context over here, so we will delete this context sizing and do another one, this one, to be context sizing, and sizing to be 0.5 mm, and generate. I think it will take some time, so let's change the context sizing to 1 mm. Okay, done. And now you can see the element size is being gradually decreased when there is a contact appearing. As you can see over here, the elements is being getting smaller and smaller once it reaches the contact surface, and the contact surface has the finest element possible given based on our element size. Then if you have another option also, that if you go to a model and if you want to divide a specific circular entity into n number of element, always you can go to sizing, edge sizing, and number of divisions to be 50, and will generate it. So what it will do is it will generate 50 elements on that periphery. Again, we can use edge sizing for multiple edges also, and it will create a uniform mesh between them. Okay, so these are your local options. Much more options are available when you are doing meshing in detail, like you can refinement, you can add mesh control, then you can use face meshing for the mapped mesh, and you can use sizing for body as well as we have used over here for body. You can use it for edge also. If you use a specific surface, okay, over here, and then that thing is being converted to face sizing, and you can define a specific element size for that face, and it will try to mesh it with that face sizing of 1 mm elements as we have described, and it will gradually increase that element size throughout the body. You can always put a cut section on it and check the element being generated from lower side to higher side. Okay, so these were some of the options that you can add and create a mesh for your analysis. Back to you, sir.
Uh, it was very informative session. So there are some questions related to this meshings. Can you hear me, sir?
Yeah, I can hear you.
Yes, sir. The first question is, sir, how can we conduct grid independent test or grid independence test in
Okay.
ANSYS?
For that, you have to add a specific command option in the mechanical window, because that thing
Hmm.
was previously available in the APDL. But to use
Yes.
that APDL feature, you have to add a specific command in the meshing, and in that you can use the same command which was using in the APDL. You put it down over here and you will get that grid independency test result in this what we say meshing, based on either you can plot it also and you can have an actual tabular data also.
Okay, sir. So there is one more question. Sir, we are randomly taking the various values of element sizes.
Okay.
So is there any better way, or how can we choose the optimum value of the element size?
Okay, that's a nice question, because generally, whenever the students are going to try the ANSYS for the first time, they don't know that what actually the element sizing value should be, that what element
Yes,
should be, what value of maximum element size should be there, and lower element should be there. So, a
yes.
basic criteria is that, first of all, whenever you import a model,
Uh-huh.
you simply generate a draft mesh by clicking the generate option. It will automatically calculate the element size based on your assembly, and once that is done you will get a specific element size value in that window, having denominated that this is the maximum possible element you can go for the entire assembly, and all other and elements were lower than that. So first you will get a specific maximum element size. Then you check the model volume, that what is the model volume compared to that element size. And if you
Okay.
see that that thing is greater than the 10 times of your element size, you have to multiply it by 10 times. Like if I have a element size of 200 mm and my
Yes.
volume is greater than 10 times of it,
Okay.
then your element is good to go. But if it is less than 10 times, okay, like if you have a
Okay.
200 mm element and your entire body value is around 450 mm cube, at that time you need to reduce mesh. It should not be greater
Okay.
than 10 times.
Okay, sir. Got it.
That one thing is possible. Another thing that you can check is whenever you do the simulation with the rough mesh you have, like n number of elements has been divided with like 5 element sizing entire body, and your analysis is done, you have the post processing also done. And in post processing, if you see that an element is having more than 3 gradients of results, because in ANSYS it will show you the results in the gradients manner from red to blue. If a
Okay.
single element has more than 3 gradients in a single element, then you need
Okay, sir.
to refine a mesh at that location, because a single element can have maximum 2 gradients in it, not more than 2 is permissible.
Okay. Okay, sir. Sir, one more basic question is that whenever we import any 3D file to ANSYS software, so which extension is preferable, sir? IGS or step file?
If you are importing surface body, then IGS is better.
Okay.
And if you are importing solid models, then
Okay.
step and parasolids are preferable. Parasolid has two options:
Okay.
.x underscore t, which is called parasolid text, and another one is .x underscore b, which is called parasonic binary. So parasolid and step is preferable when you are going for solid models. And
Okay.
IGES and one more option was there, STL,
STL. That
stereography
is.
file. Yeah,
Oh, okay.
stereography file. That is
Yes, sir.
also divided. That is also a part of what we say match file definition. At that time,
Okay.
IGES file is more preferable.
Okay. Sir, there is one question from our student, Mr. Vivanshu Patel, in the chat box. Sir, he has asked about. He has a doubt about node connectivity while performing analysis of assembly. Is it required that nodes at junction match perfectly while there is connection other than bonded contact?
Okay, so there is a nice option given in the what we say ANSYS. I'll share my screen once again to show it to you.
Yes, sure, sir.
And we will use the same model that we have generated previously for this connection option, and it will be easier to understand for the student also.
Yes, sir.
Okay, now we have two components over here. The first one is the cylinder and second one is the rectangle, and we
Okay.
have meshed it also. That, let me open that also. Okay, this is our model which we have meshed. And now as you can see over here, there is no node connectivity between two elements. Okay,
Yes.
each and every component has independent nodes which are not being
Yes.
connected at all. Okay, At that
Yes, sir.
time, when the ANSYS is importing this entire geometry from modeling perspective to the meshing perspective, it will automatically create a contact region between two elements, between two bodies. That will be our bonded one. But if we go back to our modeling options, and in modeling, you have an option called workbench, as you can see over here. Okay, visible?
Yes, sir.
Yes, yes,
Okay,
sir.
yeah. So in workbench, you have an option of share. Okay, what basically share will does is it will check the model for sharing surfaces possible. So if two entities are being shared a common surface, then it will share those topologies. And now if I go back to mechanical and refresh my model, okay, and now as you can see, there is no context being defined. And if I mesh it, it will automatically create node to node mesh connectivity.
Okay.
Okay, so whenever
Okay.
you require to share a node to node connectivity between two components, you need to share those bodies. And whenever you are not required to connect it node to node, you can simply unshare those bodies or keep it as default, and it will create
Okay.
a specific what we say connection, bonded connection
Connection.
between two entities.
Okay, sir. Got it. So for various connections like frictional connections or no separation connections, it is not required to connect the nodes.
Because frictional, rough, and no separations are basically nonlinear
Yes.
contexts.
Yes, sir.
Those are basically nonlinear contexts, and nonlinear contexts can't have that node to node connectivity because due
Sir.
to external loading conditions, the node will be moving respected to each other.
Okay, sir.
And node to node connectivity can be defined up to specific pinball radius circle, that if two nodes are coming in that region, in that radius, then that proximity will create a contact between two nodes. Otherwise, it won't create any node to node connectivity. So whenever you are
Okay, sir.
using that non-linear contact, you do not need to give that node to node connectivity.
Okay, sir. There is one more query
Yeah.
between this connection. So when to use bonded and when to use no separation contact.
Whenever no separation is mainly used whenever you have a planar connection in your CAD system. Planar connection means two surfaces are coming in contact with each other, but are free to move on each other. They don't have any kind of
Okay.
restriction in that connection plane. At that time, you can use no separation. And if two bodies are welded together or two bodies are being tightened by a specific force or any kind of connection that is immovable, at that time you can use the bonded point.
Okay, sir. Now I think all the questions are given by you, sir. Now
And
I switch over to Mr. Chirag Desai, sir, for the vote of thanks. Mr. Chirag
Uh,
Desai, sir.
Thank you, sir. Am I audible?
yeah,
Yes, sir.
Okay, okay. Thank you, Nirav, sir, for providing me the opportunity to propose a vote of thanks. I always believe that education is the greatest journey where there is always beginning, but there is no end. And by attending this webinar, above lines are true. I am thankful to Mr. Anand Mistry, sir, founder and director of Aspire Design, Vivinagar, for sparing his valuable time for this webinar. I admire the level of commitment of Anand sir for this webinar because as a design engineer, I know how it is difficult to explain and digest the thing, but sir has explained it very well manner. I also would like to extend my thanks to Professor Nirav Rathod sir and also our SSIP coordinator, Professor VC Joshi sir, for their enormous cooperation in organization of this webinar. I would like to extend my sincere gratitude to our principal sir, Dr. LB Chaudhary, our head of department, Dr. KB Rathod sir, and entire SVPS family for providing this beautiful platform for arranging this webinar. I am also grateful to all the participants from RNGPIT, other institutions, industries for attending this webinar. Anand sir, we are hoping for the favorable response in the future also. So stay
Sure,
home,
sir.
stay safe, and keep learning. Now, your concluding words, sir. Anand, sir.
Thank you for giving me this opportunity and this platform to share my knowledge to the students, because I still remember in 2004 when I was at Tajpur in the diploma college. The only thing which was new to us was solid edge. Siemens solid edge version 6 was there, and we were
Yes,
amazed by it, that how a 3D model can be generated so quickly, and we do not need to generate any kind of 2D drawings for that. It is being generated automatically. We were so amazed.
sir.
And after 10 years of journey in this CAD universe, I am finally able to prove myself. Thank you.
Sir, now we have authorized training center. That means SolidWorks campus here in our institute, in our campus, RNGPIT, for SolidWorks.
That he is also my colleague, Mahek. I know
Yes, sir.
him personally. We worked together previously.
Okay, sir. Thank
Yeah.
you.
Thank you, sir.